Start. So I'm very happy to introduce Daniel Edgington-Mitchell from Monash University. He received his PhD back in 2013, I believe, from the same university, and also spent time at Stanford during that time. He works broadly in fluid mechanics, and especially in aeroacoustics, and he's talking today about some topics that he's made major contributions to over the last few years. He also recently received an Australian Research Council Future Fellow, which is this very nice program where the government buys out some of your teaching and service duties and allows you to really focus on research as a faculty member. So without further ado, Daniel, please go ahead and take over.
All right, well, thanks for coming, everyone. Thanks for the introduction, Aaron. So normally this talk is both telling you about research and have the idea of trying to recruit some master's students. So are there any master's students here, or are we all PhD? Postdoc. Yes, all right. I have an audience for the sales pitch at the end. As always, to start these things, just some quick acknowledgements to the Australian Research Council for funding support, and also the US Office of Naval Research and the NCI for some of our computational time. Anytime a professor gets up to give a talk, really, they're just taking credit for a whole lot of work done by graduate students and postdocs. So again, just want to acknowledge some of the team, especially Dr. Petronia Noguera, who's postdoctoral fellow in our group, who's done a lot of the stability work, and Joel Waitman, who's done a lot of the experiments. And when we get to this talk, which is all about stability and experiments, you might wonder what my contribution was if I've just said that they did most of the work, but I synthesized it, sure. And a bunch of undergraduate and PhD students there. And also, this work is very collaborative. So you'll see at least one familiar face there, and if you work in jet noise at all, a lot of familiar names. Peter Jordan in France, Kilian Leitner in Germany, Tim Clonis at Caltech, someone you may recognize, Aaron Town here from Michigan, and Andre Capulet from Brazil. So this is actually a project that's run across 4 continents, which is really fun until you're trying to schedule a Zoom meeting that everyone can be at. At least 2 people are going to be miserable either because it's very late or very early, but we mostly make it work. And really, these people have, particularly Aaron and Peter, have been involved in almost every significant thing I've done on this topic in the last 5 years. So the thing I mostly want to talk to you about, the topic that I've been working on since I was a PhD student, is the topic of jet screech. And jet screech is something we've been studying since the 50s. Alan Powell first discovered it. And interestingly, even though sort of the most notable characteristic of jet screech is it's this high frequency, high intensity tone, when Powell first took his measurements, he didn't have a microphone with sufficiently high frequency resolution, or rather measurement range, to measure the tone. So he actually saw it in Schlieren imaging before he ever actually was able to record the acoustic signature. This is quite a remarkable video taken in the 60s by Poldevart et al. Looks an awful lot like the high-speed videos that we produce now, except they did it without the ability to record at high speeds. They did it with some very nice phase averaging techniques and tricks. And later in the conversation, I'm going to claim to have produced the first visualizations of shock leakage as a sound production mechanism. But now we know what to look for. Honestly, you can go back to work they did in 1969, and right here, you can see thing that I was very excited in 2021 to claim to be able to see. So what do we know about screech historically? Well, its single most known characteristic is it produces discrete frequency tones. There's an acoustic spectrum with what should be decibels per strahl on the vertical axis and strahl number on the horizontal axis. And these peaks, which are rising 20 decibels above the broadband at very specific frequencies. So it gives it a really unpleasant tonal character. Certainly at the laboratory scale, it's particularly unpleasant because just by our good fortune, it happens to hit the same sort of frequency range they use for sonic crowd dispersal weapons. So it's at the kind of frequency that messes with your balance, with your emotional regulation. Had some really fun times in my PhD taking measurements where I just burst into tears in the middle of taking data. Some of you might say that doesn't sound weird at all. What PhD student hasn't done that? But then you turn off the jet and all of a sudden you're okay again. Like, well, that was unpleasant. So we know that screech is tonal. It's discrete frequency, high amplitude. We also know that these tones are highly directional. So what we have here on the top is a map of the fundamental tone's directivity pattern. This is upstream, that's downstream. You can see very little radiation in the sideline at 90 degrees. Most of it goes back up towards the source. On the bottom is the first harmonic. If we go back, you can see that there's the fundamental and there are a couple of harmonics. The harmonic has a very different radiation pattern, with the strongest radiation being in the sideline. These tones sometimes exhibit discontinuous changes in frequency. So this is from Mancinelli et al., a paper on which Aaron is one of the authors. And it's just a really nice scan through jet Mach number. This is on a purely convergent nozzle. And you see that as we vary the Mach number, we get a continuous shift in the frequency right up until we don't. And then it jumps to another branch, and then it jumps, and then it jumps. And this is typical of resonant systems. We often see this behavior where as we change things, there'll be this discontinuous change in frequency. But in screech, it's perhaps a little stranger than it is in some other systems, because sometimes these changes are associated with change to the dominant azimuthal mode of the jet. So the A1 branch, for instance, is characterized by what we call M equals 0 mode. It's a donut, it's a toroid, whatever, however you want to describe it. In an azimuth, it's the 0th mode. And then when we get down to, say, B, that's a flapping mode. The jet flaps like this, and the axis of the flapping rotates seemingly at random, but it has a particular character. We jump up to C, that's a helix. We go back to D, that's a different flapping mode, or it's the same flapping mode, who knows? But between, say, A1 and A2, we get another one of these discontinuous jumps, but they're both the M equals 0 mode. So clearly these changes are not just driven by changes in dominant azimuthal mode. Sometimes they are, sometimes they aren't. And another thing that we know is that screech sets up a very strong standing wave pattern. So this is just essentially root mean square of intensity fluctuations from a Schlieren image, and you can see this strong lobe structure due to interference between the downstream propagating wave and the upstream propagating wave. So that's a bunch of stuff that we know about screech, and this is all stuff that we've known for a long time. We've known about its directivity, its tonal character since the 50s, the standing wave 70s through to the 90s, the azimuthal modes since the 50s and the 60s. This is all well known and well understood, but it leaves us with a lot of open questions. So Powell first, as well as discovering it in what was really a very impressive paper, also built a model to explain the physics that he saw. And his model was based on equally spaced monopoles located at the shock cells in the jet. And this is just PowerPoint. I haven't been able to sync these up to get the actual effect here, but his model assumed that these were spaced and the frequency was chosen such that you would get constructive interference and the strongest radiation in the upstream direction. So, you can get a superposition of monopoles. You can get other sources like this. That animation's just stolen from Southampton. And in the directivity plot we put up before, the symbols are experimental measurements and the lines are the predictions from a 3-monopole model. So able to match the directivity pattern extremely well.
Can you comment on that model a little bit?
It's just assuming that if you put monopoles at the location of the shock tips and you're assuming the shocks are equally spaced and you assume that there is a structure with constant phase velocity to give you a given relationship between these sources, the frequency will be selected such that the upstream radiation is the maximum.
Why'd you choose monopoles? Just
the simplest source, I guess. Nothing was really known about the character of the sources at the time, because again, he didn't even have acoustic measurements. He only had what he'd observed in the Schlieren originally. And he went with this model that seemed to reproduce the directivity patterns they later went on to measure, and also gave a prediction for the frequency of the screech tone, which is that it's related to the shock cell spacing, the convective velocity, the convective Mach number. And that prediction works extremely well a lot of the time. The alternative model wasn't proposed for a good 30 years after Powell's original model. Now, I don't know, how many people here are working in jet noise in some capacity? Anyone? Aaron? Well, for those of you who do, the name TAM is either famous or infamous. really, really talented mathematician. In Tam's world, everything is a wave. And so he's like, monopoles, nonsense, they're not monopoles. This whole model is wrong. What you actually have is a stationary set of waves that are shocks, a traveling set of waves that is the Kelvin-Helmholtz wave packet. And you can look at their interaction in the wave number domain. Very, very different physical underpinnings of the model. But this is the predictive expression for the frequency that it comes up with, which, looks a little bit different to the one we just saw. Except actually the only difference is this one is expressed in wave number and the other one is expressed in wavelength. If you re-express that in terms of wavelength, you get exactly the same prediction. So for 30 years, we had two models on a very different physical basis that predict the exact same frequency and the exact same directivity pattern. And if you're trying to figure out which model is real and their predictions are identical, it's difficult, right? So both of these give us the same prediction. Who's right? People in both camps, lots of arguments, etc., etc. So both models explain frequency and directivity. They both struggle when there are those discontinuous jumps, but if you just go through the A1, the B, the D mode, they're almost perfect if you've got the right parameters. We have some understanding of why mode staging might occur. These are some predictions from linear stability theory, and they show that this is predictions for m equals 0, this is predictions for m equals 1, growth rate of the Kelvin-Helmholtz. We see that at low Mach number, you get a much higher growth rate for the m equals 0 mode, and then as you go up in Mach number, we'll see at about sort of Mach 1, we expect equal growth rates. As we go above it, m equals 1 starts to dominate. So yeah, it sort of makes sense that you'd see this shift in azimuthal mode, but it still doesn't give us any explanation for why we have A1 to A2 or B to C or C to D. It only really gives us this one step. So a lot of open questions. Monopoles or trading interaction between waves. What causes the sound? Where does the staging behavior come from? And something really unpleasant about Screech is it's incredibly facility dependent. It's not just that you might measure one thing and someone in another lab might measure another. You might move your nozzle from one part of the room to the other and get a different Screech tone, which is just death to good science, right? You've got that little reproducibility. So this is what these questions, I guess, have been driving me since, I was doing my PhD on this topic.
I have a naive question. So folks like, Sarkar derive transport equations for pressure fluctuations, right? So let's say locally the pressure fluctuations are produced or dissipated based on these mechanisms. Mm-hmm. To what extent is that useful in this context? Because you're asking questions about sources of sound production, where I would think that these equations should point to or provide some insight on what the sources might be. Are you familiar with these?
No.
Okay, so you can imagine you can take Navier-Stokes, you could take ideal gas or whatever, and you can rewrite an equation for the pressure variance, mm-hmm. right? So you have PDE, and it's all local. And then just like with the TKE budget, you have, locally where the divergence times the pressure, whatever, this is a source, this is a sink, which is different than like acoustic analogy where you're saying I have stuff going on here and how does it affect mm-hmm. here? It's all local. But I would imagine it would at least help point to like, if you locally you're producing pressure fluctuations, this will tell you what's causing those, what are the mechanisms creating those local pressure fluctuations that probably affect pressure fluctuations that radiate outward. Aaron, am I crazy? I mean, that would be the first thing I would consider.
You're not crazy. I think the hard part will be distinguishing between the radiating and non-radiating components of pressure there, because okay. The part that radiates is a very small fraction.
0.0001% or something.
So even if you know exactly how the pressure fluctuations come about, actually distinguishing what part of that is relevant is going to be very difficult.
I see.
So classically, when we talk about resonance, we would say you can divide it up into 4 separate processes, right? You've got some downstream propagating wave or wave packet, and in this case, that's the only thing that puts energy into the resonance. In this case, it's an instability deriving it from the mean flow. Downstream, you have something which, specific to this problem, we've called a generation mechanism, where some fraction of that energy gets converted into a wave and go upstream. it propagates upstream, and then likewise at the upstream boundary, some amount of this energy can be converted into a wave that goes downstream. And so a few years ago, this was sort of the accepted model for how things work in jets, put it in my own review article, and then subsequently went on to show quite quickly that this maybe wasn't a very good model through some of Petronio's work a few years later, which is the danger of writing review articles, I guess. But early on, we thought, let's have a look at each of these processes separately, and maybe if we understand each of the individual processes, we can understand the whole thing. And if you look at images of the jet, you can sort of see this stuff in action. You can say, okay, there's, you know, when the shocks interact with the vortices, or the vortices interact with the shocks, it seems to produce some wave that we assume is the feedback wave. If we go back to the nozzle lip, we can see the waves are getting back this. Maybe there's a receptivity process. The wave packet itself is fairly clear. So those same sort of stages seem to be present here. Likewise, in impinging jets, and really it's mostly just an excuse to show that lovely color Schlieren image on the right, we expect to be able to see the same sort of thing, these same 4 stages of resonance. And the thing with impinging jets is the tonal characteristic of them is much, much stronger, makes some of this stuff easier to see. So that was the historical picture when we started looking at it, and now we say, what can we do with modern tools? So whether it be the fact that we can image things at millions of frames a second, we can run high fidelity numerical simulations, or at least have friends run them for us and send us the data. What can we do in terms of sophisticated ways of decomposing that data? And then what can we learn from linear models? And really it's the fusion of all of these that have allowed us to sort of answer some of those open questions. So firstly, one of the things we set out to do was try and look at this receptivity process. And on the left, there's a screeching jet. We'll ignore that for now. Look at the impinging jet on the right. So this was over 10 years ago now. This was at the time one of the fastest cameras in the world, 1 million frames a second, zoomed all the way into the nozzle lip. So as the schematic indicates, this part here is the edge of the nozzle. You can actually watch a wave come in, hit the lip. You can see an initial sinusoidal perturbation and a very rapid roll up into a Kelvin-Helmholtz vortex. So this at the time, there were all sorts of theories about how this receptivity process worked. And once we looked at it, it was just a pretty classic shear layer receptivity. You hit something with a perturbation. I guess the only difference from this and the sort of way that someone like Aaron might like to think about this is that incoming wave is at 190 dB. It's not very linear, right? It's more like hitting it with a sledgehammer and seeing how the shear layer responds. But nonetheless, you can see it, you know, forces a bunch of stuff in that shear layer, it rapidly rolls up into a vortex. So in the impinging jet, it seemed pretty clear what was happening. We looked at the exact same operating conditions. We took the plate away, and a screeching jet can't see anything happening. Is that because it's a weaker feedback process, or because it's a different mechanism? At the time, we assumed the former, now not so sure. So, to go with the attempt at a punny title, I'm a dad now, so I've got puns everywhere I can. I've heard the most shocking things about aeroacoustic resonance. So the first shocking thing to hear, the upstream part of the feedback isn't an acoustic wave. You'd say, but you just showed a picture that had an acoustic wave with feedback wave. And this is my own image where, you know, you can quite clearly see this upstream propagating acoustic wave. So how can you be claiming that that's, you know, this has just been a given for 70 years. Of course, we can measure this acoustic wave in the far field. It's a resonance process. Of course, it's the acoustic wave that causes the feedback. But the first hint that this might not be the case, so this wasn't really looking at these resonant jets, was in another paper by Chris Tam, one of the sort of iconic papers in jet noise, where he said, as well as the Kelvin-Helmholtz mode that you're all used to looking at, there are these other waves that can be supported in compressible jets. Now, to illustrate this, I'm going to take one of Aaron's images from his subsonic resonance, resonance core of subsonic jets paper. And here we have an empirical dispersion relation that they produced from some simulation data. And I've just used Photoshop to illustrate the parts of this that I want. The red line is the signature of the Kelvin-Helmholtz wave packet. So we have frequency versus wave number. the Kelvin-Helmholtz has a phase velocity that doesn't significantly vary with frequency. So positive phase, positive group velocity, there it is going downstream. Highlighted in blue is one of these other waves that Tam and Hugh identified. They did some stability calculations. In Aaron's paper, they do like 15 different stability models as well as the decomposition of the LES. And if you haven't read that paper, you should. It's one of the most important papers in jet noise. But the key thing about these other little signatures is they only occupy very discrete frequency bands. Kelvin-Helmholtz, in this flow, you can find it, I won't say all frequencies, but all frequencies considered here, we can see a signature of it. That's a pretty wide range. This other mode has negative phase velocity, negative group velocity, and only exists for finite bands of frequency. So it's taking energy upstream only at certain frequencies. So this wave has become sort of the hot topic in jet noise lately. And just, again, I'm spending time talking about Aaron's paper here, but they were able to show that at conditions where this wave was supported by the flow, they also found peaks in the near field pressure spectra, which was something that prior to this, I think they'd seen this in experiments 10 years prior, and everyone assumed it was just a mistake or a facility effect. And it was only in this work to say, oh, hang on, there's actually something happening in the flow that might be driving this. And as I said, lots of different stability models in that paper. And one of the really nice things they were able to do was put in models with different levels of complexity, which included or didn't include different things, and get predictions that matched extremely well with what they saw in the data. And on this basis, they were able to figure out that these were some of the waves that Tam and Hugh had described, as well as some others that were active in this jet. Okay, so that's all well and good for the subsonic jet. What about above Mach 1? Well, we knew that this wave had a particular structure. We knew it only existed for finite frequency bands. At this point, I'd like to be able to say, and I was the first person to show that it was in a screeching jet, and I was beaten by the French by a few months. They put a paper out first, which, using simulations, showed some evidence that it was in the flow. But look at that terrible, boring, black and white color map. We used a lovely, beautiful color contour, which means they got rejected from JFM and we got the front cover, despite the fact that they did it first. So life's not fair. We did it with experiments and stability modeling. They did it with numerics. But to be fair, they did get there first. And then since I got distracted making fun of them, I should actually talk about the significance of this. The white lines here are predictions from, it was a model that Aaron had put together, where we expect this wave to be neutrally stable. And the color contours are where we see the screech tone. And you can see that we're not worrying about these because this is only the m equals 0 prediction. It sharply cuts off at both the upper and lower limit. You do not get screech tones outside this range. And
so screech tones are defined by just above some decibel?
Yeah. Yeah. And in this case, we haven't used a threshold. We're just showing you the raw data so you can see where they are yourself. But we used to say, oh, if it's 10 decibels above the noise floor, we'll call it a tone. But that's so arbitrary that what you're going to throw away one that's 9.7 and
right.
So now we just show the raw spectrum and you can see where they are for your own satisfaction. When we predict now on a model based on this, we get much better predictions than we used to with the old models. So we've done a bunch of work on this since. Everywhere we've looked, we find that this mode is there. So this, as an example, is from actually the first paper that Aaron and I worked on together, where we took non-time resolved PIV data and did a whole bunch of decomposition steps and filtering and then reconstructed and tried to pull out what these modes actually looked like. And I guess the key point here is the downstream propagating wave, it's the Kelvin-Helmholtz, looks exactly like you'd expect. The upstream propagating wave, quite strong fluctuations in velocity, but no vorticity. This is not a vortical wave, it is an acoustic-like wave. I think we even called it an acoustic mode in this paper, which we no longer do for reasons we can discuss later. So this is more in the hope that this might be of use to a non-jet noise person. How do you find a traveling wave with non-time resolved data? So the approach we took was to do snapshot POD, build equivalent Fourier modes from the POD, do a Fourier decomposition in the axial direction, filter it, and then reconstruct. So one of the reasons I continue to work on resonance is it's a lot easier when your flow is resonating to use this sort of approach, right? This won't work if you can't pull out snapshot POD modes that capture the dominant structures. But in this case, you know, if we plot the mode coefficients against each other, they form almost a perfect circle, signature of a traveling wave. That part is easy when the flow is resonant. We build a complex mode from our two real POD modes, just mode 1 plus I times mode 2, and we assume that these modes represent a fluctuation happening at the screech frequency. We can't get the frequency from this data, we can just stick a microphone in front of the jet and find out the frequency. Now that we have a complex mode representing a convective wave with a given velocity, we can do a Fourier transform in the axial direction and produce its, before we had a dispersion relation frequency versus wave number, this is at one frequency, but we can also get it as a function of the transverse position. And so then we can see structures associated with the Kelvin-Helmholtz, the upstream mode, other modes that we'll talk about in a moment. And then we just do a very crude bandpass filter. And we can say, all right, well, if we filter around here, this is the amplitude distribution. This is the shape of that mode. This is the amplitude distribution of the Kelvin-Helmholtz, and just a picture of the Kelvin-Helmholtz. And when we first looked at this, we found this other weird one up here, which was confined to the core of the jet just in a certain region. And we didn't know what that was, so we called it the blob mode, because it looked like just a blob of energy in our wave number spectrum. This is the Australian blobfish, symbol of national pride. And just, it's always important to clarify, it's not its tongue, that's just a parasite that's lodged in its mouth. So we spent a while just not knowing what this is, so we called it blobby, and presented at conferences a few times with blobby, but we did end up working out what blobby was, at which point we had to sort of stop using this image, which is very sad. So what we eventually ended up showing was that the wave that goes upstream is this guided jet mode from TAMQ. The wave that goes downstream is a duct-like mode, which had really been the focus of Aaron's work in the subsonic resonance paper, but we found some evidence for it here too in the supersonic jet. Now you might say that's a lot of decomposition steps. You've taken data, you've done snapshot POD, built a Fourier mode, assuming you know the frequency, done a Fourier transform, filtered it, and is that actually valid at all? Well, this was, again, where collaboration is really important, because Aaron and one of his students here did a global stability analysis on the base flow that we provided. And without any need to talk about the intervening time, we ended up with this amazing result. The intervening time there is where Aaron's students spent a year trying to figure out why the results didn't match before we realized that I'd sent them incorrectly scaled experimental data. Because if you take one thing away from today's talk, if you're trying to measure distance on a ruler, you don't count the dots, you count the distances between them. Yeah, that's right. Otherwise your collaborators waste a year. We still talk to each other, so it's okay. This was, to me, remains sort of one of the most remarkable results I've been involved in producing, because they produced this from a time averaged mean flow. And they threw it into their global stability model. And this is the distribution in wave number space from the model, and this is the distribution in wave number space from the experiment. And the fact that in a shock-containing, screeching, resonating, highly nonlinear thing with nothing but a base flow, they were able to say, this is where all the waves will be, this is what they will look like, and get it right, still sort of blows my mind. So funnily enough, here we actually use the global stability analysis to validate the approach to the experiment, because there was so much decomposition required to get this out of non-time resolved data. Now, is the upstream wave in jet resonance always a guided jet mode? No. If you have a nice big impingement plate down the bottom, you get things that are very, very clearly shock-like waves coming outside that you can just watch in the high-speed Schlieren, and you can see them hit the nozzle and produce the downstream propagating wave packet. So not willing to say in every form of resonance it's this guided jet mode, but everywhere else we look, so this is a twin supersonic jet with big, strong shocks, that's the comparison between the prediction for the guided jet mode and the experiment. This is in an elliptical jet. That's the prediction between the guided jet mode and the experiment. Every shape of jet, every combination of jets we look at, we find this same thing over and over again. And we don't find resonance when we don't find this mode. What produces the guided jet wave? Where does it come from? This is the other part of the resonance picture. So now we go back to, PAL versus TAM, monopoles versus wave-wave interaction. And what we found is if you want resonance in jets, you need shocks. The shocks will have some wavelength. You need a downstream propagating wave packet. It will have some wavelength. And in TAM's model, you can just say, well, the shocks are basically just a sine wave that doesn't move, and the wave packet's basically just a sine wave that does move. And that's all you need to build a prediction here. You don't need to worry about anything else. So the way that works, let's imagine we have a stationary wave, and then we have some traveling wave going past it. It's just going to infinity in every direction, no amplitude envelope, nothing at all. Then from TAM and TANA's work, the triadic interaction between these two waves should transfer energy to two other wave numbers given by the sum and the difference, which would look something like this. It will give you a wave going upstream, it'll give you a wave going downstream. And you've already seen that this is exactly what we're able to find in data. So despite being built on a model of just, constant amplitude waves going to infinity, this model for the triadic interaction does describe what's happening in this flow. And so that's given us sort of our current understanding of resonance. And again, just to emphasize that this triadic interaction is really what happens if we take the Kelvin-Helmholtz and we sum and subtract the shock cell spacing. That's exactly where we find energy in our data. And same thing for the global analysis. Global analysis doesn't know that it's supposed to do this. It just does. This is just what comes out of the linearized equations. So I'll just then sort of link this to how we might predict screech to occur from a purely stability analysis perspective. Here's a dispersion relation where you've got the Kelvin-Helmholtz wave packet, you've got the upstream propagating guided jet mode, a strange creature we've just been talking about. And if we say, well, we assume that there'll be energy redistributed by this triadic interaction, because the shock cells have zero frequency, this is just a direct offset of the Kelvin-Helmholtz. And then we just look for where this intersects with the guided jet mode. And when it does, we say resonance should occur. So that gives us a frequency, and then we can go to our experimental data, build a model on this basis, and we find we consistently get within 2% of the screech time doing this. And we can predict different mode stages as well, for reasons we'll come back to at the end. So what have we learned so far? Triadic interactions between the Kelvin-Helmholtz wave packet and the shocks energize the guided jet mode, which is what closes the screech feedback loop. It's not a phased array of monopoles. It sort of is what Chris Tam thought it was in terms of wave-wave interaction, but he had the work showing the guided jet mode exists, he had the triadic interaction work, didn't have the two together. So it's actually two separate pieces of work by Tam that we've sort of smushed together that seems to explain screech. It still doesn't give us staging or where the sound comes from or anything else. So where the sound comes from, this is the shocking part of I heard the most shocking thing. This is not a screeching jet, this is the exhaust of a pulse detonation engine that I work with a team in Berlin on. And this is essentially a starting supersonic jet. And the reason this is nice is it really beautifully illustrates what can happen to shocks in the presence of very strong vorticity. And this is just running forwards and backwards to hopefully give you lots of opportunities to trace what's happening with this shock here. It's trapped in the starting vortex of this jet. As the vortex moves away and the shock starts to move towards its quasi-steady situation, you end up with a whole section of shockwave that just gets left outside the boundaries of the jet in almost quiescent fluid. And you can't have a stationary shockwave in quiescent fluid, right? That's like gas dynamics 101. When you have the normal shock equations, you've got to have an upstream Mach number greater than 1. So through the action of vorticity, you end up with this section of the shock in a place where it can't be sustained in a stationary sense. It's going to have to propagate. That's the only way to satisfy the governing equations. And that's exactly what you see happening here. This section of the shock ends up outside the jet, propagates initially as a shock wave, and then as it decays, will eventually become an extremely strong nonlinear acoustic wave, and then far enough, a weaker acoustic wave, and so on. And so that's really a nice illustration of what could be happening. It's sort of jet screech writ large. People have theorized that something like this happens in screeching jets. This is some work from Sanjeev Lele and his students at Stanford, where, without getting into the details, some really beautiful work showing that everything from a DNS to a geometrical acoustics model predicts that the saddle point between vortices in a shear lag will cause the shock to leak out of the jet, and then some of it will dissipate, or not dissipate, some of it will transmit away as an acoustic wave. And so ever since I started working on this topic, I wanted to see this happen. And eventually we were able to do so, though as I said at the beginning, maybe now if you go back and look at Poldervaart 1969, it was already done. But we had this nice high-speed Schlieren where, if it's just playing on loop here, so, hopefully you can convince yourself that you can see the vortex comes through, a bit of the shock moves, the acoustic wave comes off. And for probably 8 or 9 years, I had videos where I believed that you could see this happening. I'd show them at conferences and people would mostly be convinced. Few holdouts. But then you try and turn this into something you could put in a journal paper, a series of still images, and it looked like a bunch of random noise. Because these are not, if I was, actually I can't pause this because it's, I can pause it, there we go. Look, shock leakage. Somehow people weren't convinced. So what we ended up doing, taking a leaf out of the decompositions we were doing for the other work, is we applied the same sort of Fourier decomposition on the image data. So we did a decomposition in space and time, and then just filtered out anything that had a positive phase velocity. So the image on the right is intensity fluctuations that can be characterized as moving upstream. And so what you get is a whole lot of nothing right up until you get one of these shock leakage events where the shock moves back and transmits an acoustic wave. And so this gave us what we needed to be able to put it in a series of images and have a reviewer look at it and say, okay, yes, that thing actually is coming from the shock. It is going upstream. And we're able to visualize this in a whole lot of different jets, axisymmetric, non-axisymmetric, etc. And the other really nice thing in that work is, as a follow-on to some of Lele's work, one of his students had gone on to build sort of a ray tracing geometrical acoustics model saying, oh, look, we can predict that shock leakage will occur. And they did that with synthetic flow. We took our actual PIV data and having to do a lot of hand waving along the way, because these acoustic particles that you inject here that obey the ray tracing equation are meant to mimic the shocks. Our data already had shocks in it that we had to then sort of smooth out, but keep the vorticity fluctuations. We put their model into data and we found that it basically predicted shock leakage to occur at the same place we saw it happen in the Schlieren. So this theory that they developed, early 2000s at Stanford, and the model they developed, we combined it with real data and we got a prediction that matched what we saw in the Schlieren. So sound is coming from these shock leakage events, which are not included in our triad interaction model. In impinging jets, as an aside, we can also see these transient shock-like structures that form in the wall jet, and we can trace these waves all the way back to the nozzle. It's the work of Joel, who's a postdoc with us at the moment. This was part of his PhD. But then there's also shock leakage-like mechanisms in impinging jets. So some of these systems have multiple sources of sound, and trying to differentiate between them and figure out which one is active is quite difficult.
What's the role of baroclinic torque? You have all these curved shocks that probably producing vorticity locally.
I remember looking into that years and years ago, but with the sort of data that I had access to, now with high fidelity simulation data, you might be able to say something about that. With the sort of data I had, I remember looking at it and just saying, I can't say anything about this.
What are these Reynolds numbers?
500,000. Ish, 250 to 750, we'll say. All right, so I think the last shocking thing, and this is still very much an open topic, one of the things Aaron and I have been talking about this morning, Another assumption we've always made in Screech is it's when the wave hits the nozzle, the upstream wave hits the nozzle, that we get the downstream wave. But in some of Petronio's work, he said, well, I'm building these local models, and then I'm sort of, artificially saying, well, what happens if the flow has shocks in this static interaction? What if I could do that in a single step? So he used a flow K ansatz for his stability model, and instead of having a local model, he had a locally periodic model. So he said, what if the base flow is periodic by construction? A flow with shocks is sort of periodic. It's not strictly periodic, but it sort of approximates it. And the really interesting result he got there was this guided jet mode and the Kelvin-Helmholtz mode in a locally parallel sense cannot form a saddle point. But once you include the periodicity of the base flow, they can, which is what we're seeing here. This is in the straight lines come from the locally parallel calculation, and the curved lines where we're getting this saddle come from the locally periodic framework. Did I just say periodic twice? Locally periodic. And when we look at the wave numbers that are predicted in this locally periodic framework at the saddle point, it looks a lot like what we're seeing in the data. And Petronio used this to then say, okay, well, if there's a saddle point, it can be an absolute instability. What frequency would this occur at? Oh, and I've removed that slide for time, but essentially, again, got within a couple of percentage points of the Struhl number in the experiment with no tuning, nothing from the experiment, just matched the periodicity to the shock cell wavelength, nothing else, and nailed it almost exactly. And this model goes to infinity in either direction. There's no nozzle, right? And it still predicts that we will get an absolute instability at the right frequency with the right structures in it. Same time, in an experiment, if you go and thicken your nozzle lip, the screech tone changes. So clearly the nozzle matters, but doesn't seem to be a requirement. If you could have a jet that went forever in either direction, maybe you wouldn't need a nozzle, but in a real jet, maybe you do. Aaron's got some ideas for how we might be able to figure that out. And so the last thing, our most recent piece of work, existing models were very good at getting A1, B, D. Tam could get it perfect. And they always had to use some fudge factor to get the A2 and the C branches. But it turns out that those predictions would have worked fine with one change. So we've talked before about, we have shocks, you can characterize them by some wavelength or some wave number. Okay, well, if you stop looking here, that seems like a reasonable thing to do. If you look further down, you can see that both the amplitude and the spacing start to vary quite rapidly. If you take a Fourier transform, and this is 0.6 diameters, relevant in a second, take a Fourier transform in X and you plot the spectrum, it looks something like that. So if you have a wave of constant wavelength and decaying amplitude, that will give you a spread peak in the spectral domain. If you also have a variation in spacing, that will be represented by a series of suboptimal peaks. Here we have both. So yes, the peak wave number here is exactly what you would expect based on the spacing of these first few shocks. But it's spread, and you can see there's at least 3 suboptimal peaks to capture what's happening in this region. There's also a harmonic, that's not relevant for here. So when we talk about the wavelength of the shocks or the wave number of the shocks, which wave number do we mean? Okay, the peak wave number, sure, but that is not significantly more energetic than other wave numbers around it. And we do have these other peaks. So when we talk about a triadic interaction between the Kelvin-Helmholtz and the shock cell wave number, which shock cell wave number? The peak? Well, that's what everyone did for 70 years, was just assumed that you could just take one number to represent the shocks. And once again, my brilliant Petronio, who within 6 months of looking at Screech for the first time, answered the question I'd been working on for 15 years. Not bitter, very grateful, not bitter. He figured out that if you take a spectral representation of the shocks and you get all these suboptimal peaks, if you consider a model built not on the primary peak, but the secondary peak, predictions with the primary peak, predictions with the secondary peak. These jumps that are not associated with the change in azimuthal mode are associated with changes in which part of the shock cell structure the feedback is coming from. So this just blew my mind when he showed me this result. Like it's the advantage of having someone who's come from a very different perspective. I was an experimentalist originally. I think in terms of physical space. He thinks in terms of wave numbers. And if you've got a series of shocks, of course you want to represent them in the spectral domain. And look, there's all these other peaks. It's quite obvious. Let's try a different one. There we go. So the other component here that had always bugged me personally is we have this standing wave. And if you just assume constant velocities of the two waves, then you can relate the frequency to the wavelength of the standing wave trivially from a mathematical perspective. And Panda published this work. He said, oh, we should use the standing wave instead of the shock cells to, as the length scale for screech. But this result isn't based on physics, it's trivial maths. You have two waves, this is what will come out. Now, if we generalize this, put it in terms of wave numbers and just upstream and downstream wave speeds, we can see that it looks exactly like Tam's expression, which we've had plenty of reason to support now, except one has the standing wave number, the other one has the shock cell wave number. So if both of these are true, there's a pretty trivial next step, which is that these should have the same wave number. So do they? Well, a lot of the time, with an experimental uncertainty, they do. This is some work from Bertrand Mercier. And the most right-hand most column is what we're looking at here. I keep trying to use the pointer, but of course it's a screen, it doesn't work. And you can see within a couple of percent, they agree. Across the whole parameter range, they swept, except that these two cases were out significantly. And it just so happens to be that that is the A2 branch of screech. So that is A1, it matches, A2, it doesn't, B, it does. So in the areas of screech where the classical models do well, K-shock and K-standing wave match. But when the mode jumps occur, we switch between it matching and not matching. So then we might, linking back to Trent's work, say, but what K-shock are we using? And so that led us to, in our most recent piece of work, a hypothesis that all stages of jet screech can be predicted from the model of TAM if we're willing to consider multiple peaks of the shock cell wave number. And the corollary to that is we should always be able to satisfy this relationship if we can consider multiple peaks of KS. So how did we test that? We took a very large high-speed Schlieren database. You can just average it in time and then take the spatial transform. That will give you all of the peaks of the shock cells. We can then apply SPOD, popularized by some guy. I don't know. He's done some more artwork, I guess. If we take the absolute value of the SPOD mode, that gives us the standing wave. We can then take a Fourier transform of that, and that will give us the wave number of the standing wave. Or we skip that step and we just do our Fourier transform on the complex SPOD mode. That will give us all of the waves that are active in the flow, the carbon Helmholtz, the guided jet mode, etc. So that's what we're going to use to test this hypothesis. So we used a really ugly nozzle, which was good because it gave us a lot of weird tonal behavior that allowed us to test the theory. We did it on round jets, elliptical jets, rectangular jets, high aspect ratio rectangular jets. These are all SPOD spectra here on the Schlieren. So as an example of how we get out the shock cell wave numbers, these are plots of the shock spectra against operating condition, and we teamed up with a group from Tsinghua who had a really nice data set that they'd taken with a similar camera to ours. Their nozzle was more classical, ours was this hideous little tiny thing sticking out of a flat plate. So as we scan through nozzle pressure ratio, this is how the shocks change. This is how the spectral representation, those first two peaks change on the right. So took all that data, stored that. Then we take the absolute value of the SPOD mode. We do the same thing where we perform the transform now on the standing wave and we pull out the standing wave number. And you can see that staging behavior here, those discontinuous jumps, the standing wave changing as we hit those conditions. And when you looked at the shocks, you didn't see discontinuous changes in the fundamental shock cell peak. And then we plot those against each other, and this is what we get. In the A1 branch, it matches shock cell in black, matches red, KS1, A2, matches KS2, B, matches KS1, C, matches KS2. On two different facilities with two very different nozzles. Screech is famously facility sensitive, which was why it was so nice to be able to say, countries 10 hours apart by plane, you get the same result. It's a general result. We went on to show that it's true for elliptical jets, rectangular jets. In high aspect ratio rectangular jets, there's no mode staging because there's no KS2 peak. The jet mixes out so fast that it's represented by a single shock cell. Set aside the standing wave, our sort of final piece of evidence was let's just do a transform of all of our SPOD modes. What do they look like? Well, here's something where we're in the B mode, something where we're in the C mode. So that is the acoustic wave numbers. And you can see that far from the jet, we've got acoustic radiation where you'd expect it to be. Going upstream in the core of the jet, the energy is at higher wave numbers. It's not going upstream at the speed of sound, it's going a bit slower. If we then put on our predictions from the triadic interaction between the Kelvin-Helmholtz and the two shock peaks, we nail the upstream peak almost exactly for KS1. KS2 in this case is not doing anything interesting. For 3.2, where we've had this staging jump, we can see the interaction with the fundamental shock peak doesn't get anywhere close. But once again, the interaction with KS2 nails it almost exactly. So we sort of showed it in the roundabout wave in comparison to the standing wave. This is the direct evidence that the resonance can be closed both by an interaction with the primary shock cell peak or with the secondary. And there it is across like the whole range. The cyan now, I switched the colors, apologies. The cyan now is acoustic, and we can see that the dominant energy is never going upstream at the speed of sound. It's always a little bit slower from a pressure ratio of 2, barely screeching through to 4, big mark disk in the flow, quite different physics. We either get good predictions from KS1, KS2, always slower than the acoustic wave. So as a sort of final point on that, again, this messy nozzle with sometimes as many as 4 peaks, when we go and look at these peaks, we found 2 modes that were m equals 0. One, the energy is at KS2. The other, the energy is at KS3. The other one, m equals 1, KS2, KS3. 4 different screech peaks, none of them closed by the classical assumption that it's to do with the dominant shock cell wave number. So on that basis, one of the things to tick off your bucket list is to publish a paper called The Unified Theory, right? We didn't feel we were quite there, so we called it a unifying theory. And one of the reviewers says, no, you can't call it that, it's too strong. I said a unifying theory, and the editor sided with us, so we got it published. So
unless you're Detlef, it's hard to get away with it.
Yeah, and look, to be fair, we haven't answered all the questions, but we thought we were pretty close. So, you know, unifying, we're going there together, you know. A unifying theory, not the only one. So triadic interactions between the Kelvin-Helmholtz and regions of local quasi-periodicity in the flow associated with the shock structure represented by peaks in the streamwise wave number spectrum. These interactions energize a range of wave numbers, including the guided jet mode, which propagates upstream to close the resonance loop. The rest of it we'll leave aside for now. I'm not sure how I'm doing for time. Okay, I think for now. So, some general closing thoughts on this part of the talk. So, empirical wave number spectra are a very useful tool. I can say it was seeing Aaron do it in his paper that really sent me down the whole path I've taken here, which is one of the reasons I love that paper so much. You don't always need time-resolved data to calculate them. This was the thing we did that was new relative to what Aaron and his co-authors had done. They had this beautiful large eddy simulation database. I had a bunch of PIV taken at 0.3 frames a second in a jet whose characteristic frequency was 10 kilohertz, right? So truly randomly sampled data. Linear stability theory has no business consistently working this well. We violate all of the assumptions that you make when you build one of these linear models. Our flow's not parallel, it's not linear, and somehow it just produces predictions that nail it time and time again. And Aaron and I have been having a big talk about the guided jet mode, and really at the heart of a lot of our approaches is that your reduced order models are valuable not for what they include, but what they throw out. Because when you build a model that's nothing but a spring and a mass, and you capture the physics exactly, you know that nothing else matters. It's just something represented by a spring, something represented by a mass.
So did the last 2 points, does that point to, if you were to look at maybe lower Reynolds numbers where the flow is less invested, is it possible that you'd have more nonlinear effects and turbulence is more important and it breaks down? Have you
People have done this at Reynolds numbers of like 1,000 and still seen the same overall behavior.
The key, I think, is that you're linearizing about the mean. So all the nonlinearity is built in. I mean, the influence of the nonlinearity on generating that mean is there. And now you're looking
Yeah,
at,
but if your variation about the mean is large, right, so the whole idea, like that's when it doesn't work.
in principle, but I think what we found is that these parts that we're interested in are such a small part of the overall turbulence that they act almost linearly.
Okay. And as an aside, if anyone's working on other projects, I'm also interested in detonation engines, jets and crossflow, rocket nozzle resonance, which is sort of, we're hoping the next frontier for Screech, because we seem to see something like Screech in rocket nozzles during startup. That's how to get the next bit of funding to keep working on the same thing I've been working on for all this time.
Does that include any multi-phase or particulate?
Absolutely not. I've got to crawl before I can walk, before I can run. So we'll see if there's actually anything down this path or whether it's more an interesting lab scale problem with no relevance. So the other thing I wanted to do was particularly something that Aaron and I have been talking about for a while. I think people here don't tend to think about Australia for grad school because you're already in a country with the best university system in the world, right? But there's a lot of reasons that you might want to consider coming to us. So firstly, as a place to live, Melbourne has ranked in the top 10 cities in the world to live in every year for the past 12 years. We did take first place 7 years running. We were also the most locked down city in the world during COVID. We beat Buenos Aires by a bit most days in lockdown. So somehow we're not number one anymore after being locked inside our homes for 18 months. But it is a fantastic place to live. Extraordinarily multicultural city. The food's amazing, nightlife's really good. Socialized medicine, no guns. Various other nice things. So Monash as a place to study, I have some random pictures of our nicest buildings. Again, you know, when you talk to people in the States, look, we don't get offended by the fact that often we're not that well known, but we're now ranked in the top 50 in the world in both overall and engineering. If you want to use the US news one for a bit of local flavor, we're ranked even higher. Number 1 or number 2 in Australia for engineering, depending on which ranking scheme you're using. Look, 42 in the world, you might be surprised how many big universities in the States that puts us ahead of, right? We're certainly not ahead of Michigan. Okay, this is a top 5 in the world, not top 50. But, you know, we're pretty happy for top 50. The university is only about 60 years old. So, you know, we're very proud of that fact, at least. So what are the opportunities? Why might you come there? What do you get for a PhD scholarship in Australia? So you get $33,000 per annum tax-free. Now, I know what you guys are getting here in American dollars is better than that, but it's not tax-free. But what might be of more interest, any work that you do as a TA is paid $51 an hour on top of that. What's minimum wage here again? So, look, I'm not claiming that our PhD students are living lives of luxury, but it's perfectly livable, right? Perhaps the biggest difference between our system and the system in most of the rest of the world is your PhD scholarship is yours. It comes from the Australian government. It does not come from your university or your well, one tier comes from the government, another tier comes from the university. Very, very few come from your supervisor. Which means if you don't like your supervisor, you can leave.
So there are the projects, you have like industry funded PhD projects?
A tiny minority.
Okay.
Because there's no industry in Australia. In aerospace, if you're not doing composite structures, there's just no industry funding. So there are downsides to our system as well. Our work is generally less tied to industry. Which is good and bad, right? Harder to have direct impact, but we, you know, talking to, I was at Virginia Tech before this, and all of theirs are industry funded, and they have grad students who have to meet with their project officer on a weekly basis, give a presentation every week. We don't have anything like that, right? you can pick, I mean, you've got to find a supervisor who's willing to work on the project you're willing to work on. But the key thing for us is the power balance is completely different. We have more scholarships than we have students. So academics are begging, no, come work in my lab. No, come work in my lab. Any project you like, you know. Where would you like your office to be? Not quite, but it's a very different system to the States. I spent some time at Stanford in grad school here. I've seen one side, but it is quite a different feeling. And one of the things that I've been talking about with Aaron for a while, if you come out of Michigan with a master's and a decent grade, you are going to be extremely competitive for one of these scholarships because this is a top 5 university in the world. And you may be able to be co-supervised by someone here. So all of my students now are co-supervised by leading academics somewhere else. The downside of Australia is we're a long way away, right? We're a small country, a long way away. So the way I try to give my students that international sort of focus is they're co-supervised by someone in Europe or the States or South America. So, you know, you could be supervised jointly by someone like Aaron. You could even come back here for some of the time, but still be funded by the program in Australia. It doesn't mean you can get a Monash scholarship and just come back and live in Michigan for the next 5 years, right? You will still need to dominantly be based in Australia. But let's say that you're a really good, bright student. There's someone you want to work with here, they just don't have funding for you at the moment. This is something that you might consider. You might still be able to work with that person jointly at a university that is still, you know, top 50, in a place where it's a bit warmer. Though no, Melbourne is not known for its great weather, but it doesn't freeze at least. So whether this is of interest to you or to anyone you know, we don't get many applications from the US. We get a few from Europe. We get 1 million per day from Iran. You can't open your inbox without applications from Iran. I mean, a country that really values education, right? We get a lot from China and Southeast Asia. We get very few from the States. And it may be, for some people, this could be a really good option. It's a good place to live. And, you know, we're a small country, but our research is reasonably well funded. And you do get a bit more freedom than you might get here. And of course, you know, what you all really want to know is if I come to Australia, will I get to see all your crazy animals? So, yes. Here is a definitely real photograph of one of the engineering buildings. You know, kangaroos, koalas, wombats, echidnas. That's Eddie the emu. He just lives on top of the building and plays with me sometimes. Just where's your next JFM? No, I mean, Melbourne is a big city. The university is in the suburbs of the city. So sadly, you won't have any of these running around. But half an hour drive. An hour, maybe. All right. If you'd like to talk about that further, I can either talk to you about it today. You can send me an email. Otherwise, questions about any of it. Thank you very much for listening.
Thanks for the great talk. So how can you use this information to mitigate screech in jets?
Great question. So the terrible dark secret behind all of this is screech is not a problem in real jets. Screech is actually really easy to get rid of. You just mess up the homogeneity of the flow in like any way and screech goes away. I mean, the possibly apocryphal story is a professor pointing with a screwdriver and accidentally pointing into the flow and the screech tone just going away. And I have tested, you can just stand there and go, like, it's not hard to get rid of. So why are we still talking about it? Primarily because when you have 2 jets next to each other, the coupling between them means the screech comes back. And this has caused failures on the F-15, the B-1B. And so that's the whole reason I'm here is because we're funded to look at it in twin jets. So how do you get rid of it? In twin jets, if they're coupled this way, that's really bad. If they're coupled this way, it's not so bad. So part of what we're trying to do is see what you need to do to ensure it's in this, because then you get a pressure cancellation rather than an aberration. You stick tabs in the nozzle, you stick chevrons in the nozzle. They're both very good at killing shocks. If you kill the coherence of the shocks, you kill both screech and broadband shock noise. But, you know, you want to suppress all forms of jet noise without amplifying others, and that remains difficult. And certainly if you're on the military side of things, you're like, oh, I can get rid of your noise problem and it only costs you 0.2% of thrust. And get out. We're not interested, right? It's got to be no thrust penalty, all the savings. That's good.
How does this relate to crackle?
It doesn't. Crackle, you need a hot jet, so that's been out of our reach.
Okay.
My understanding is the current work on crackle is suggesting that it's just these really intermittent local events where one little bit of vorticity is spinning around and convecting faster than the others, and some simulations by Christophe Bogie and his team, you can see this really nonlinear wave come off it. Crackle looks like it's produced by shocks in the near field, but not the sort of steady shocks we have here, shocklets that form due to the movement of local bits that flow. That's my understanding as of a couple of years ago.
So I've heard it described as the third order moment of the pressure distribution function, like this. Is that correct? Right.
That's a way to.
It's a description.
It's a description of it. Yeah.
No, is that a correct description? A way to.
I mean, that's just a measure of the nonlinearity of an acoustic wave, right? So it's a way to infer the steepness of the wave, and crackle is thought to, the thing was, is it a nonlinear steepening as the wave propagates, or does it start out nonlinear?
Sure.
And currently, I think the idea is it starts out nonlinear. It doesn't become nonlinear as it propagates. But crackle's not my area. It's just what I've seen at conferences.
All right, if there's nothing else, then
Anyone going to come to Australia?
yeah, feel free to chat more after we close officially here, but we're a bit over time. So
Is there anyone online who wants to ask?
there were a bunch of people, but they all left.
All right. Well, thanks again for coming.
Thanks, Dave.